So good afternoon. It's a pleasure to introduce today Luisa Toledo. She joined us recently at the beginning of the years. Of this year, she studied at Campinas, the degree in physics, also master in physics, and completed it in 2018. Then she has completed a PhD at the Trinity College in Dublin, and the presentation of today represents most part of what she has been doing during the PhD, and she is now working with Gonzalo, Gianluca, and myself in the National Plan Project COCUSI. So, please.
I have one here. Thank you. Okay, hi everyone. Thanks. Yeah, so the talk is going to be about this project that I worked on my PhD, which is on thermodynamics of driven dissipative condensates. But before jumping into my work, I will start with some motivation. So I will introduce what are Bose-Einstein condensates and non-equilibrium condensates as well. Then a little bit about heat engines and a motivation to my work. Then the two systems that we looked into, which are polaritons and photon condensates, and then conclusions. Okay, so Bose-Einstein condensates are these macroscopic, is this state in which you have macroscopic occupation of the ground state. The idea is that you have a box with a thermal gas in equilibrium, and there is some thermal agitation, and as you cool down the gas, this thermal energy decreases, and you get that the interspace between the molecules of the gas gets smaller. Then when you reach some critical temperature, the interspace becomes comparable to the de Broglie wavelengths of these particles, and they overlap. So then you have the collective phase, which is characterized by long-range spatial coherence and a sharp temporal coherence of emission. Then I put here some examples of systems in which we have driven dissipative condensates, which are excitons, phonons, polaritons, photons, plasmons, and magnons. And these are some examples of, these papers are just some references of examples of when these were obtained experimentally. The idea of the non-equilibrium condensate is pretty similar to the equilibrium one. So you have a gas of particles and you have some cooling mechanism, but now we also have some losses. And because we have losses, we need some pump to overcome this. So if you have a condensate with loss and pump, then this can happen in 3 different regimes. So if you have that the losses are very small, so that you have time for the particles to actually thermalize here before you lose them, then this is pretty much similar to the equilibrium condensate. But you can have another case in which you would have this coherent emission, but the losses are faster than the cooling mechanism. So you don't have thermalization of the gas, you don't have time to thermalization, but you have the coherent emission. And in this case, the system is behaving like a laser. But then you also have this intermediate regime in which these two timescales are comparable. And so you can have the condensate, but you can have maybe partial thermalization, but you don't have full thermalization of the gas with this cold source. Okay, now slight change of topic. Heat engines. So heat engines is the device that takes energy from a hot reservoir to produce some work and dump the excess energy in a cold reservoir. What we know about heat engines, they respect the laws of thermodynamics, of course. So the first law is conservation of energy. And for the second law, I put here this Kelvin-Planck statement, which basically says that you can't have work produced just with a hot source. You also need the cold reservoir. Now, when we go to the quantum regime, not so much changes. The first thing is you're going to have a quantized amount of energy exchanged with the engine. And the other thing is the laws of thermodynamics, they stay the same, but now on average. There is, though, this other consequence of the second law, which is that not only you're going to need 2 heat baths, but also they are going to exchange different amount of quanta with your engine. And because of that, if you want a machine operating in steady state, then you need at least 3 levels. So here I put, just for completeness, definitions that we're going to use for heat and work. So this is the heat current is due to changes in the density matrix of the system, and the power due to changes in the Hamiltonian. Okay, so this seems like I'm talking about 2 different things, but what we did was exactly to put this all together. So we showed that when you have this coherent emission, regardless of what regime you're in, we can see that as a work output of a heat engine. And we look into that to both microcavities with polaritons and photons, and show that because you have this heat engine, then we can constrain condensation using the second law of thermodynamics. Okay, so now I'll start with the polaritons. But of course, first I have to tell you what is a polariton. I don't know, maybe you don't know. So a polariton is a particle that is part light and part matter. The idea is that you have a microcavity, so you have these 2 mirrors, and you shine light into the cavity, and it's going to interact with a semiconductor here. And if this interaction is strong enough, then you don't have photons and excitons, but you have a superposition of both. And these are the polaritons. So this is the Hamiltonian. You have energy of the light. Here is the energy of the excitons and the interaction term. And we can see the Hamiltonian of the polaritons by diagonalizing this. So you just define this as a combination of these 2 other operators. And you can show that because excitons and photons are bosons, then these other 2 operators also respect the commutation relation of bosons, and you get this Hamiltonian, which is the Hamiltonian of 2 free particles, the upper polaritons and the lower polaritons. I put here the dispersion curve of this. So in dashed, you have the dispersion curve of the excitons, and in dotted, the one of photons. The dashed one looks almost flat, but that's just because when compared to light, the excitons are very heavy, of course. So then this is the upper polariton branch, and this is the lower polariton branch. And here, I'm in front of. And here is the excitonic and photonic fraction of the lower polariton branch. So you see that for higher momentum, they are basically just excitons, which is here. You can see that they coincide. And then as you get to lower momentums, they become a mixture of photons and excitons. I'll be just focusing on the lower polariton branch. Okay, and why are polaritons is interesting? That's exactly because they are hybrid. So because of their excitonic part, they're going to interact more with each other, which means that you can have nonlinearities because of that. And because of the photonic part, they have a small mass, which means that, well, the temperature, the critical temperature for condensation is inversely proportional to the mass. So because these particles are part photons, they're lighter, which means that we have higher critical temperatures. And actually, you can have polariton condensation even in room temperature. And the other point is that then also because they're photons, they escape of the cavity and they have a smaller lifetime. So that's why the system is out of equilibrium. This is the first polariton condensate that was obtained. So you can see as you increase the pump, this is in the momentum space and this is in the space. So as you increase, you have accumulation of polaritons in the ground state. These are just some of the applications. So you can use them to optoelectronic devices such as lasers, switches, and transistors, but also you can use them to study collective states. such as synchronization, vortexes, and superfluidity. Okay, so as I told you, we have this microgravity, and the polaritons are these hybrid particles that are part light and part matter. In one experiment where we obtain condensation, usually the protocol is to shine a very high energy laser, so it's non-resonant with the polariton states. So this is the dispersion curve that I showed before. It's just like one side of it. And we shine the laser with very high energies there. This is going to excite electron and holes, they thermalize, and in the end, you form excitons. Then the next thing that happens is that they're going to thermalize with the acoustic phonons, sorry. So they emit phonons and they can relax through this dispersion branch. But the problem is once they reach this region here, they become more photonic, which means it's harder for them to interact. And so they accumulate here. This is called a bottleneck region. And they can't actually keep relaxing just through phonon emission. So what happens is after they accumulate here, they interact with each other, forming one high energy polariton and one low energy polariton. And well, there is radiative decay here because it's more photon-like. And if this scattering can overcome the radiative decay, you have the condensate. And also, of course, that's with the radiative decay is important because that's how we get information of what's happening. We have the microcavity and we're measuring the light that comes out of it. Okay, so that's all well known and well established. What we did was we tried to take this and build a minimal model that contains all these features. It's a 3-level model, and it's a heat engine. And this working medium of the heat engine has these states that are squared over there of the polarity. So note that the condensate is actually not part of the heat engine. Okay, so I'll go like a level by level. So the first level contains a number of particles there at the bottleneck. Then it interacts with a hot reservoir, which is this pump here that's putting energy in the system. And you get n+1 polaritons in the bottleneck. Then they are going to interact with each other. And if you have a condensate, then that's macroscopically occupied and that's stimulated emission. And you can do a mean field approximation. So then the condensate is treated as a classical field. So the idea is that this is the Hamiltonian, so we have the energy of the 3 levels, and this is the interaction with the condensate. Well, because that's a classical field, and if you remember the definition that I showed before of power, then you can see that this is going to cause changes in the Hamiltonian, and this is going to be the type of energy exchange here is of work. Okay, then we have one particle went out of the heat engine and the other one to the high energy state here, and it thermalized with phonons back to the bottleneck. That's the cycle of the heat engine. The other thing is because we are adding a new particle to the system, there is also chemical potential associated with this hot reservoir, which is a thermal reservoir of excitons. And so this energy is split between work and heat. Okay, so we had the model, we calculate the stat, we can derive the master equation for it, which is a Redfield equation. We can calculate the steady state and we can get heat currents as well using counting field statistics. I'm not going to go too much into the details, but this is kind of a schematic of the transformations we made to calculate this. So first you have the 3-level system. These are the spectral functions. Then when you go to rotated bases, which is the Foucault bases, you have that you get replicas of this with plus and minus omega. So this is E3 minus omega, and this is plus omega. So you have these states. And then you go to eigenbases. These are all mixed states of the previous one. So they all interact. And you get that the heat currents are going to be some rates times the energy that's exchanged. So the hot exchange these two energies and the cold these two energies. Well, the rates are kind of a big expression, but the main idea is that you have one term that corresponds to a semi-classical just scattering. So you have the stimulated emission and the absorption, and then you have this other term here, which is some sort of interference term that you get from the Redfield equation. Okay, but remember that, so that was the steady state of this heat engine, yes? But there is also, the heat engine is populating the condensate, but there is also the losses, of course. So we haven't considered losses so far. So what we did next was we considered that there are many of these three-level engines in the cavity. They're all populating the condensate, and there is loss of the condensate out of the cavity. Then the actual steady state of the system is such that the amount of particles populate that are like going to condensate, or the gain of the condensate, is the same as the loss. I have a plot for that. So you have, this is the number of particles in the condensate, which is proportional to the strength of the classical field that we are using to describe it. This is the loss, which is just a linear loss because it's radiative loss. And the growth is the power output divided by the energy of the condensate. So it's the quantity of energy every time you populate the condensate. And the steady state is when they both cross. The condensate is the classical field, yes. Here? Yes. So it's a classical field, and the number of particles, this comes from mean field approximation. So like if you take the square root here, you get the ladder operator, let's say. Yeah. Okay, so then now we calculate the steady state of this whole thing, and we get the number of particles in the condensate as a function of both the hot and the cold temperatures. We see second order phase transition in both cases, and they reach like a maximum for certain temperatures. But the most important one is this one, which is the phase diagram. So it's a phase diagram as a function of the hot and cold temperatures. So this is for different decay rates of the cavity. So the idea is below this, you have condensation, and above you don't. So the interesting thing is, as you get a better cavity, let's say with smaller losses, we get closer and closer to this red line, which is the reversible limit of the heat engine. So basically what it's saying, what this plot, like what this phase diagram says is, so to have condensation, first we need that this heat engine is operating as a heat engine, producing work. So it needs to be below this, but also if we have losses, then it also needs to overcome these losses. So then you would need, I don't know, even colder temperature or even hot temperature. Okay. These are just some other results, which I don't think I want to go too much into details, but this is to show that we can also get a first order phase transition. The idea is that if you have more nonlinearities, then, well, in black is that curve that I showed before of gain, and in red is the loss. So if you have more nonlinearities, the gain curve has this shape that is just like, woo. And so the loss curve crosses it twice, and you have stability, and because of that, you can have first order phase transition. The next, we calculated the power and efficiency as a function, both here parameters of the hot reservoir, so chemical potential and hot temperature, and here as a function of the coupling strength with both hot and cold. From all of this, the main one is this one, which shows that it doesn't change a lot. The power output doesn't change a lot when you change the coupling with the hot bath, but it changes when you change the coupling with the cold bath, which shows that the thing that is controlling the speed of the thermodynamic cycle is the cold reservoir. Okay, and then the other thing is that, we can also have condensation with this heat engine operating in different modes. So as I said, remember I said that this was both heat and work. So because of that, we can, depending on the chemical potential, we can have that, for example, the work input is greater than the work output, or the other way around. And we can also then change the temperatures of the hot and the cold reservoir. So here are the 4 possible regimes. And this is the plot. This is another phase diagram as a function of chemical potential and the temperature of the cold of the phono reservoir. So the idea is, in one, this is the case where there is more work output than work input, and we're taking energy from we always take from the exciton reservoir to the phono reservoir. But in this case, the exciton reservoir is colder. So we would be taking cold to hot and producing work. That's illegal. So we can't have condensation here. The second one is when is the same direction of energy, but we're inputting work. So that's allowed, and that's a refrigerator. And we can have condensation here. So the gray, again, is the diagram where below you have condensation. The third one is the heat engine, which is the one that we already see. And that's just a dissipation regime where you have input work, but the heat flows in the normal direction. Yeah, and here the interesting thing again is, as you get to smaller losses, you cross this point here where the phase diagram, where the line of the boundary of the phase diagram crosses from heat engine to refrigerator without dissipation, because that's a reversible limit. Yes. Yes. There is always here in the 3 possible cases, there is always some increase in the condensate. But the difference is that the input heat, the input work is greater or big. So if you're inputting work to produce work, then it's like you're just dissipating energy, maybe, you know? That's the difference. Yeah, I mean, that's also fair, but it's just a different mode of operation. So you can have a condensation here, or here, or here. That's what I mean. Yes, yes. No, the condensate is always in that direction. It's just what changes is just the chemical potential. Yes. The yes. So you can kind of forget about the photons and excitons. Just think of polaritons. So you have the polaritons, and they have different energies. So this, the 3-level system is the different possible configurations of the polaritons. And then, the hot reservoir is adding new polaritons, high energy polaritons. Yes. Yes. Is cooling. Yeah. That's the idea. Yeah, in this case, it's not cooling. Yeah, that in this case, that's the, yeah, it depends on the region. Yes. Yeah.
The omega is produced by what? By the energy of the condensate? I think there is a frequency there.
Yes.
Which is right in the side.
Ah, yes.
The reason why
The
steady state at the front of the state, getting the rotating frames.
Yes, in the rotating frame, of course, yes. This is the frequency of the condensate. Yes, which is the classical field. So the idea is that you can think of the condensate as the same as a classical field.
Classical
Yeah, it's oscillating. But because I'm doing everything in the rotating frame, nothing is oscillating.
then so steady is a cycle. And then the heat
Mhm.
is the heat is produced because in the non-rotating frame you have a time dependent
Yes.
of the
Yes.
The time dependent is by the Hamiltonian field.
Yes, yes, that's the idea. The idea is to kind of because these driven dissipative condensates have been debated a lot if they are lasers or not, or if they're condensates. And the idea of this work was to say that fundamentally they are lasers, because you get to this model where this is basically a three-level laser. It's the same model that you have for a three-level, the basic three-level laser model. So that's kind of the argument. Any other questions? Okay, I will move on. I was actually done now with the polarity, so we can go to photons. So the photons is a similar idea. But now we have a microcavity and we have a dye in the center instead of a semiconductor. And the photons interact weakly with this dye. So when you have emission from the cavity, this emission comes from photon states and not from polariton states. So you don't, this coupling is small, so you don't have polaritons. That's the difference. Then what happens is, well, a condensate of photons is kind of a hard thing to get because photons don't conserve the particle number when they interact usually. So you need to find some interaction in which they conserve the particle number so that you can cool them down. And that's what the dye does. So you have this microcavity, you have some input laser, and this is the rate of emission and absorption. Blue is emission, sorry if you can't see it. And this is absorption. And you see that in general, what happens is the laser comes in here and it's going to be trapped there. And the photons interact with the dye. So excites the dye and re-emits, excites and re-emits several times. And with that, it cools the photons. So you can see that on average, the emission it's emitted with less energy than it was absorbed. So you get that they cool down. And they respect that Kennard-Stepanov relation. Okay, this is just the experimental result in which they got. So as you increase the pump, you get some population here is in momentum and he's in space, and you have accumulation of photons in the ground state. So we use this guy's model to model this, which is way simpler than the polarity model. It's just some rate equations. So this is all just semi-classical. We have the number of particles in a certain mode M of photons. And this is the probability of the dye being in an excited state. So the dyes are these two-level systems, but they have some vibration degrees of freedom as well. So then these kinetic equations have, let's go term. So they have some radiative losses. This is the interaction between the dye and the photons. And they also show in the PE. And we have some pump. First, we started with some pump directly in the dye. So the pump is exciting the dye molecules. So with this, we wanted to, I don't know, look at some thermodynamics. So what we did was looking at this expression, but for m equals 0, so for the ground state. So if we do that, we get to this expression here, and if we divide the emission rates divided by the absorption rates, we get to this expression, which if we just take the logarithm, we get to this. That's the point. This one is some entropy flow to add particles in the condensate. And you can see that this looks pretty much like a heat engine. You have, this is the heat flow from the hot reservoir, this is from the cold reservoir, and this is some other heat flow, which is just due to the particles, to the particle flow in the system. And that's quite interesting because it was just a totally different path to again get to a three-level system, because also these energies are, you just have these three energies that even though we had a lot of degrees of freedom, we end up that these are the ones that matter. So you get something that's pretty much the same as before. This is a simulation, so the number of particles in both condensate and the total number of particles in the gas, well, they overlap because this is just too big. And the red line is the reversible limit of the heat engine. So the condensation happens precisely at the reversible limit. That's because the losses are quite small in the system. Huh? Yes. Yeah, it's quite hot. That's true. I mean, that would be the temperature of a laser that you're putting into excite the dye. Then we started wondering, what if, okay, so this is how, if you have a laser as a pump, but what we wanted was to have a proper heat engine. So we thought, what if you can do that with sunlight? So we swapped this laser input by a thermal source. And we wanted to see if you could get condensation with this thermal source. Then the equations are pretty much the same, but the pump changes. Okay, we can calculate the same thing for entropy, but now it's just not so straightforward to interpret. And we calculated again the same plot. In red here is the reversible limit for the other one, which is the one that we actually had an expression that made sense to call it a heat engine. But I just put here for comparison. So anyway, the condensation happens when there is a macroscopic occupation of the ground state, which is the dashed line. So we see that we need a hotter reservoir, but we actually can have condensation. I mean, it's less than the temperature of the sun. Yeah, that's true. Then we compared the two different types of pump. Again, the red line here is just for comparison, is that reversible line. In purple, the dye pump, and in green, the thermal pump. First, okay, let's go. This is just the logarithm of the previous plot, but I wanted to put them both together. So you see there's a very nice phase transition in the first case. In the second case, it's not so nice, but you do cross the line of this red line here, which means you have condensation. This is the chemical potential. So we see that we reach the chemical potential expected if you have condensation. And this is the efficiency. So efficiency is the dotted line is the Carnot efficiency. And we get the Carnot efficiency for this one, which we already knew, okay, it matches the reversible limit. But for the green one, which is the thermal pump, is always less than the one before. And we actually have a kind of a justification for that. If we calculate the heat current, you have that there is no heat current for the first case, the dye pumped one, until you reach the reversible limit, and then you have the three. But in this case, because you're pumping in all these different modes, it's almost like you have all these different energies being exchanged at the same time. And because of that, you can have heat currents even without power. You just have energy going from hot to cold without having power. And so you have more entropy. And so you can never reach the reversible limit. So even before, so here, when you have a power output, be when you have a condensate. Even before that, you already have some heat current. So that's why this is more irreversible, let's say, than the other one. That's all I was gonna say. So just take-home message is that if you have these driven dissipative condensates, then you have some coherent emission, and you can map that into a classical field, and that's work. So then we can use thermodynamics and the second law of thermodynamics to try and get conditions for condensation. We did that for polaritons and phonons, and we get these different regimes. And yeah, that's it. Thank you. Yeah. There is music. What?
I had a curiosity about the methods. At the end, you could describe everything with rate equations.
For the phonon one, yes. For the polariton ones, we use master equations.
But then when you were showing the equations, it seemed like the coherencies were not playing any role. You could actually have a reduced description only with the N and P, just because we have approximated, or?
No, for the polariton ones, they play a role here. So this would be the semi-classical. We have this other term here that is interference term. I don't know.
Okay, okay.
So in this case, it was more like that. Sorry, it was.
Okay, okay.
So thank you. So do you think it may change something if you instead of considering the condensate as a classical field, you really so you have a quantum mechanical description of it? Because here, so if it is like a classical field, it's like you're assuming there is no back action on the condensate because of the interaction with the machine, no, with the thermal machine.
Yeah.
But in reality, of course, you will have some kind of back action, no? And so, so I was wondering if you went also into this kind of description, like more full quantum mechanical description.
No, in this case, no. We just looked at that. The idea is that this model only works sort of for like the limit where you already have a condensate. You couldn't, because you're doing this mean field equation, with this mean field approximation in the field, you can't use this to describe like how to get to the condensate or anything like that. You already have this steady state where there is a condensate.
Okay. And other question is, if did you look at the variances of the currents, or how this?
I haven't looked actually. I thought of at some point, but in the end, I don't know. We were just more focused on the polariton than on.
Okay.
I thought of getting the like how's it called, uncertainty relations in this case, but I didn't.
Okay. Yeah. Perhaps this is interesting. I don't know how much they will be kind of violated here, but in the usual tree-level measure, you can have violations of the TUR. And
yeah, it would be interesting to look at.
More questions or comments? No. So if not, let's thank the speaker again.
Thank you.